Hey, yo kids, you wanna buy some drugs?
What are drugs?
What do they do?
Oh, they're great. They make you feel unstoppable. You're gonna feel like you're on top of the world.
That sounds good, let's do it!
Wait. How much do they cost? And how long will this feeling last?
Well, that's the thing, you just don't worry about it. I would just buy some and just take them, Just don't worry about it.
That's a good point. Like, we can do some simple drug delivery tests and find out how long it would stay in the system.
Yeah, well they better last long, or I'd just rather get drunk.
Hey, listen kiddos, I just deliver the drugs. I don't tell you how they're delivered.
Drug delivery has garnered much attention in recent years due to its ability to accurately manipulate the rate of delivery by controlling drug transport through capsule manufacture. In this experiment, hydrogel beads are synthesized and tested to observe the transport phenomena of drug delivery from a bead into an aqueous system. Certain variables are altered to observe their effects on rate of delivery and gain a better understanding of the transport processes in the system. By analyzing the experimental data, information such as the type of rate constants associated with the system can be calculated. With this information, better delivery systems can be designed to meet the needs of various patients. In hydrogel drug delivery, there are many factors influencing the release of the medication, or in this case, dye. The two primary methods are diffusion and relaxation of the hydrogel beads. Overall, the diffusion of the dye through the gel bead into the solution can be modeled with Fickian diffusion and be described with these equations. Equation 1 is Fick's law of diffusion, showing the dependence of solute concentration on position x, time t, and diffusivity d, a property of material pairs. By applying Fick's laws to hydrogel drug delivery systems, equation 2, known as the Ridger-Pepos equation, can be used. In equation 2, the fraction of solute released is equal to k, a kinetic rate constant, and the time raised to a diffusion exponent, in this case 0.4 to 0.5 for Fickian diffusion. In the event of Fickian diffusion and bead relaxation, the exponent will be greater than 0.5 to a maximum of about 0.85. Any value higher than 0.85 represents a mechanism where relaxation effects are much greater than Fickian diffusion effects. While accurate for many different bead geometries, this equation only adequately represents the first 60% of drug release data due to other competing processes that can affect the geometry and diffusional gradient. Equation 2 can then be linearized into equation 3, and using the collected data, the rate constant k as well as diffusional exponent can be obtained with graphical analysis. In order to test the beads, tartrazine, which is a food dye, was used to imitate the drug. This will be released from cross-linked beads which are manufactured by mixing a calcium chloride and tartrazine solution with an alginate solution. The calcium ions help the alginate to fold around the tartrazine solution, creating beads with trapped dye through the cross-linking process. In order to test the factors affecting the diffusion rate, 3 variables were altered based on previous knowledge of diffusion properties. The first alteration was bead size. Diffusion is a flux process requiring an area to operate over. By altering the bead size, the surface area to volume ratio of the beads could be altered, leading to different concentration gradients, as well as different flux quantities for the overall flow of dye into solution. The second property was the stir rate of the solution. By changing the mixing rate in the beaker, the concentration in the beaker could be more ideal and evenly mixed or less ideal, leaving most of the diffused material directly adjacent to the beads. With even mixing, a larger concentration gradient would be observed, leading to more diffusion, whereas a more concentrated solution near the beads would represent a smaller concentration gradient and thus less diffusion. The third variable was cross-linking time of the beads. This process is time-dependent, and if the beads are allowed a longer cross-linking time, then the barrier to diffusion will be much higher, because the bead will be less porous, changing the permeability for diffusion. This case will also show the largest effect of relaxation of the hydrogel bead, since the longer the cross-linking time, the stronger the bonds holding the bead together. By altering these parameters, data can be collected and analyzed with equations 2 and 3 to calculate the kinetic rate constants and the diffusional exponents of the process.
So, let's talk about the experimental procedure behind drug delivery. Before beginning the experiment, it was necessary to prepare the required solutions. The first solution prepared was a tartrazine solution that contained 0.5 grams of tartrazine for every 1,000 milliliters of water. Roughly 300 milliliters of an alginate solution was then prepared by combining 3 grams of alginate with 300 milliliters of this new tartrazine solution. The solution was placed on a stir plate and mixed until a smooth, uniform yellow solution formed. Finally, 500 milliliters of a stock solution of 6 weight % calcium chloride was formed. This was made by taking a specific weight of calcium chloride and adding it to the tartrazine solution. A spectrophotometer was used to measure the absorbance over the course of the experiment. It was necessary to calibrate the spectrophotometer before conducting any of the trials. To calibrate the machine, the wavelength was first set to 427 nanometers, as this is the peak absorbance for tartrazine. The machine was then zeroed by taking an initial reading with deionized water. Once zeroed, the absorbance of 10 dilutions of known tartrazine solutions were recorded. These readings enabled us to create a calibration curve of concentration versus the measured absorbance. The curve was later used to calculate the fraction of drug released for the duration of the experiment. The calcium chloride solution was poured into a weighboat. 3 milliliters of the alginate was taken from the beaker and loaded into a disposable syringe. The alginate solution was then slowly dispensed into the calcium chloride to ensure that the drops would form beads. The drops were placed all around the boat to avoid beads forming on top of one another. When varying the bead size, we attached different size needle tips to the syringe to produce small, medium, and large beads. The beads required a few minutes for cross-linking. For the majority of the trials, we allowed the beads to cross-link for 5 minutes. However, when varying the cross-linking times, we allowed some samples to cross-link for 10 minutes and for 15 minutes. When the beads were done cross-linking, they were filtered from the solution and rinsed with DI water. Once the beads were filtered and the spectrophotometer calculated, it was time to begin the experiment. A 150 milliliter beaker was filled with 100 milliliters of DI water. The beads were added to the DI water and the stir rate was set. Most trials were conducted at a rate of 400 RPMs. When the stir rate was varied, speeds of 200, 400, and 600 RPMs were used. Each trial lasted an hour. Samples were removed with a pasture pipette and the absorbance was recorded every 2 minutes for the first 10 minutes, every 5 minutes for the next 20 minutes, and every 10 minutes for the remaining half hour. After each reading, the sample was returned to the beaker to maintain a constant volume.
The collected data for each adjusted variable consisted of absorbances measured at 427 nanometers for samples taken at various time points. Before we could analyze the data, each measurement had to be converted from an absorbance to a concentration. This was done using the calibration curve generated at the beginning of the experiment. In order to determine F, the concentration at time t was divided by the concentration at infinity, which is calculated based on total diffusion of the introduced tartrazine. Typically, F is calculated by dividing the mass of drug released at time t by that released at time equals infinity, but concentrations can be used here because volume remains constant. Only the first 60% of the data was used because the model is only valid for these data points. 3 plots were generated for each adjusted variable. The first is a simple plot of F versus time. The second is a log plot which linearizes the relation between F and T. The N and K values can be determined from a linear regression. By taking the derivative of our governing equation and substituting the experimentally determined N and K values, the instantaneous rate of change of F can be plotted versus time. When bead cross-linking time was varied, the most dye was released at a given time for a cross-linking time of 5 minutes. This makes sense because there will be fewer crosslinks within the alginate, permitting easier dye release. F was higher for 15 minutes than 10 minutes, but this is believed to be due to contamination by tartrazine at the beginning of the experiments. Stir rate did not seem to significantly alter the diffusion of tartrazine. This is not perceived as negative, as there is no analogous treatment that can be performed within the human body. When different sized beads were examined, the smallest beads had the highest F at a given time, followed by the largest beads and then the median beads. Again, tartrazine contamination was believed to have influenced these results. The N values for all trials were well below 0.43, the number which indicates Fickian diffusion. The reason for this is unclear. In an effort to improve our analysis, we attempted to fit an alternate model with 2 terms to account for both Fickian diffusion and swelling effects. We did this by setting an objective and constraints for solver in Excel. However, no feasible solution was found. It is worth noting that the beads shrank during the course of the experiment. This is surprising, as we expected that the beads would take in water and swell, potentially resulting in swelling control of diffusion. However, bead shrinkage might explain why the N values are so low.